Okay, hello everyone, and thank you for listening in on my presentation. So my name is Christoph Sydora, and I'm a PhD student at the University of Alberta in Edmonton, Canada. So the presentation today is on BIMkit, an extendable toolkit for reasoning about building information models. So as the title suggests, the theme of this paper is relating to building information modeling, or BIM. So briefly, BIM defines a set of specifications for objects in a 3D model, such as the types, properties, and relations. So more specifically, this research is focused on what is commonly known as CloudBIM. So when we're talking about CloudBIM, we're referring to all cloud-based services relating to BIM storage and data exchange. So this includes services such as storage, model checking, evaluation, design automation, and simulation. So CloudBIM inherits many of the standard cloud benefits, such as the shared computing resources and remote accessibility and scalability. So when we're talking about BIM and data exchange, the most common and standard format is IFC, short for Industry Foundation Classes. So IFC is a quite large and complex format, so this kind of results in a lot of information easily being lost when importing and exporting from one tool to the next. So as a read-only format, IFC wouldn't be that problematic, but for true CloudBIM architecture where we have multiple services simultaneously viewing and modifying a model, IFC proves to be quite inefficient. So this is especially the case for the latter model modification kind of services. So for BIMkit, our primary goals are to implement an ecosystem of some of the common BIM services, such as the automated evaluation and modification of shared BIM models. So we want these tools to be implemented in the cloud-based services, meaning they all have exposed web APIs. So it's also important that these services share the same resources and speak the same language, so to speak. So by this, we mean not only sharing the same model, but also having a single shared object catalog and a reasoning engine. So that way, when models don't differ extensively in terms of the detail and semantics from one another. So by having many of these reasoning services available, developing and testing new tools can be streamlined for future research. And so on that note, just having a simple data model also decreases the learning curve for future research development. So when looking at related work, we highlight two studies that share similar goals but differ in their approach. So one that has been around since at least 2010 is BIM Server. So BIM Server is your typical model repository. Models can be uploaded, it has some version control. The models can be viewed via their BIM Views model viewer, and also they have some add-on development options. So unlike what we're proposing, BIM Server stores its models in IFC, meaning it suffers from many of the same previously mentioned IFC drawbacks that make it pretty inefficient for the purposes of this research. So the other related study is BIM Rule Language Simplified Schema, or BIM RLSS. BIM RLSS has a number of similarities. It kind of builds off the same simplified model representation and also uses the rule language for their model checking. The biggest difference between the two are primarily implementational. So theirs was kind of constructed as an application with add-ons, while ours is based on extendable web API services, also more like microservices. So with that in mind, the first component regarding BIMkit is the building data model and how we represent the building on both the client side and on the database sides. So the goal here was to break the model down into the most basic BIM concepts. So to that point, we focused on the whole building, which is the model. And then that model contains both objects and relations. And then each object contains a type, it contains the geometry or the shape of the object, and the material of the shape components. All of these have an extendable list of properties as well. So on the model storage end, we have the BIMkit Repository. So the repository has two components to it, the database, which is implemented in MongoDB, and then the service end. So the database stores the models, objects, and materials separately, while the service sits on top of the database managing the API requests. The service has a variety of different functions it performs on the data. So the first, it controls the model user access, so who can view and edit each of the models. The second is the separation of the objects from the model. So in order to increase the design standardization. The majority of the objects are placed in the model from a preloaded catalog and then stored independently from the models. So that way, the BIMkit repository will separate the catalog object from the model-specific objects, like the walls, floors, and roofs, and then reconnect the two when the model is downloaded, when the model download is requested. So because catalog objects are separated, we included a level of detail element to each object, meaning that included in the API request is the detail of the objects that you want to download. So the reason behind this is to support the different use case needs, as some applications, such as like mobile applications, would benefit from these lower detailed objects. And then finally, the BIMkit repository can do some minor model validation as well to ensure that the necessary components are all present in the model. And in future iterations, we might add some specific semantic information prior to the request. So the first and most important use case is the actual model editor. So in its current state, we have not really implemented all the editing functionality you typically see, instead focusing on just adding objects from the catalog and then placing in the model. So as you can see here, we've selected the empty layout, and then we can select the objects that we want to place, and then after that we can rotate the objects, move the objects around, and also add some properties to the objects. So the viewer is also the primary hub for where we request various services. And then that also displays the results back from those services to the user. So as many of you may notice, the viewer was developed using the Unity game engine, and most of the service in general were developed using the .NET framework. So we also have the rule storage service, which is accessed by both the model checking and generative design services. So the rules follow the design rule language we developed in our previous study on rule language-based model checking and generative design. So rules are created using any of the three editors you can see on the right that we developed previously. They each kind of have a different user experience to them. So one uses a series of Windows forms. Another one uses some puzzle-like blocks to create the rules. And then we have a third one that is a natural language editor, which attempts to parse the natural language rule text automatically. So similar to the BIMkit model repository, we have like a rule management service for where you send the request to upload and also does some validation of the rules prior to the storage. So once the rules are uploaded, they can be shared amongst users, and then you can create your own personalized rule sets. So one of the main services for the BIM toolkit was to perform these automated model check using the rules from in the rule language. So this is where a user would select their model. They can then click on a set of design rules that the model must adhere to, and then they can send that to the model check service for evaluation. So the service then returns a report on the checks with information relating to the checks, such as the instances that may have resulted in errors. So here you can see in yellow, we have all the objects relating to a particular rule. And then when things highlight red, that indicates an instance of a failure to the rule. And we have the green instances resulting or indicating a pass. So keeping in mind that not all instances have to pass in order for the rule itself to pass. So next we have the generative design service. This automates part of the layout process. So first we would take the initial model that we want to select. And then once you have that, you go through and select the object that you want to place in the scene, or the first object. And then kind of with the same thing with the model checking, we have all the constraints that we want to check that are specified in the rule language. And then we generate the scene, it places the object in the scene, and then we would repeat this process with the next object. Same idea, we place the object somewhere in the scene, select the rule specific to that new object, and then we generate the scene and it'll automatically place that based on the requirements as best of its ability. So the actual generative design service gets the model ID from the request and then accesses the model itself from the BIMkit repository. But since the generative design performs a number of these evaluations, it's using a lot of a lower detailed version of the model. So we're specifically using just bounding boxes for this generative design and then wiggling those around the scene until it finds the best local position and orientation in the model that meets the rules that we specified. So the simulator works more closely to the BIMkit viewer, and that's a 3D viewer rather than a service. So once we have a model selected, we can select the activity trace, which is just simply a list of the agent's tasks. Next, the walkable areas are then programmatically determined based on the types and geometry of the objects. For instance, we'll find all the flat surfaces on the floors and identify stairwells and elevators in the model. So then next, the agents perform their tasks in sequence in real time, or we can just have a sped up version of the simulation. And then once we have like these fine-grained movements of the agents in the model, we can record the building usage data. So for instance, we can determine areas of higher building traffic or how long it takes to complete certain tasks for each of the agents. And then these can give you an in-depth analysis on the building and the layout, providing another form of evaluation of the model that these rule languages and geometrical rules typically can't account for. So just to put it all together, the following figure shows how each component is connected via the API they expose and the data flow in between them. So on the left, we have the BIMkit model and object repository. On the right, we have the rule repository for the rule language storage. So then both of these applications have their respective population and monitoring applications for managing the access and the content. At the bottom, we have the checking and generative design services. These access the models, objects, and rules in order to perform their actions. And then on the bottom left, we have the model simulation, which here is a separate viewing application that accesses the same BIMkit models. And then finally, we have the main kind of viewing service, which requests the various services and displays the results of the services. So BIMkit was developed with two considerations in mind. So the first is to increase interoperability between the services, all surrounding a single model store. So with that, all services are intended to access the whole model as opposed to only a view of the model as IFC uses. And that kind of ensures that we have this model integrity throughout. Second is the idea that very little can be assumed to be present in the model. So by that, we mean that we kind of started with this notion that we can only assume geometrical information from the objects, since much of the information required for checking is implicit and not directly present in the model. So to solve this, all tools rely on a shared semantic enrichment library of the model in order to perform the edits, checks, and evaluations. So as this tool matures, we kind of hope to continue to expand the semantic enrichment method library and extend the checking, and that way extend the checking and automation capabilities. So the contributions of the research are twofold. First, we outline a simple data model approach for representing BIM information and reasoning about a model. And then the second is the toolkit, which, given the variety of the tools, serves as evidence on the effectiveness of the underlying representation. So finally, just like to acknowledge NSERC Canada for supporting this research. And thanks again for listening on my presentation, and feel free to reach out to me if you have any questions. Thanks.